Here is a number worth sitting with: 5 milliseconds. That is how long it takes an autonomous vehicle's computer vision system to detect an obstacle and trigger a braking signal. 5 milliseconds from camera frame to decision. The round trip to a cloud server and back is 60 to 200 milliseconds in good conditions. On a congested mobile network, it can be several seconds. The math on that is not subtle. You cannot build a self-driving car that phones home for every decision. You cannot build a medical device that sends raw heart data to a data center and waits. You cannot build a factory line that pauses for a cloud API call while stamping out 60 cars per hour. These systems have to think at the edge, on the device itself, right where the data is generated. And increasingly, that same logic is reaching into your phone, your earbuds, your retail store, your agricultural equipment. I'm Alex. This is Bot Thoughts by Amtalk Soft, and today I'm talking to Sam about Edge AI, what it actually is, what hardware made it possible, and the practical path for developers who want to build with it. Welcome to the show, Sam.
Thanks, Alex. Edge AI is one of those terms that gets used everywhere and means subtly different things depending on who's using it. The core definition is simple. Instead of sending data to a central server or cloud to run an AI model, you run the model directly on the device where the data originates. A camera that detects defects without uploading images. A phone that transcribes speech without sending audio to a server. A temperature sensor that classifies anomalies without any network connection at all. The reason this matters is that it dissolves a set of constraints that have fundamentally limited what AI can do in the real world. Latency, the round-trip penalty of cloud inference, goes away. Network dependency, the assumption that you always have connectivity, goes away. Privacy concerns about transmitting raw sensor data largely go away. And the economic cost of cloud compute at scale, which becomes enormous when you're processing continuous sensor streams from millions of devices, goes down dramatically. What's interesting about this moment is that all three things that previously made Edge AI impractical, the hardware being too slow, the models being too large, and the tooling being too immature, have all resolved in a very short window. That confluence is why Edge AI went from research lab concept to production reality in the last 3 years.
That's the thing I want to pull on. What specifically changed? Because the idea of running AI on devices isn't new. People were talking about on-device AI 5 or 6 years ago, and it was basically science fiction for anything beyond toy examples. What actually happened?
The honest answer is silicon, specialized chips. For a long time, running AI locally meant running it on a general-purpose CPU. That is slow and power-hungry for matrix operations, which is fundamentally what neural network inference is. CPUs were not designed for this. The turning point was dedicated AI accelerators, hardware specifically architected to execute the multiply-accumulate operations that neural networks require, in massive parallelism, at a fraction of the energy cost of a CPU. Apple shipped the neural engine in the A11 Bionic chip in 2017. In the iPhone X, that single engineering decision meant that every iPhone since then has had dedicated silicon for AI inference, running at 38 trillion operations per second on the latest M-series chips. Qualcomm built the Hexagon NPU into Snapdragon, and now the Snapdragon 8 Gen 3 can run 7 billion parameter language models entirely on-device. Google's Tensor chip in Pixel phones is specifically optimized for speech and image models. For the edge server and industrial side, NVIDIA's Jetson Orin packs up to 275 TOPS, trillion operations per second, into a module that runs on a single power supply. And for the ultra-low power end, Google released the Coral USB accelerator, a tensor processing unit for $8 that adds 4 trillion operations per second to a Raspberry Pi 5. So the hardware spectrum now covers everything from a $35 hobbyist board with a USB add-on, all the way up to a Jetson Orin running full computer vision pipelines in a factory. That range is what makes the ecosystem interesting.
You mentioned that range, from Raspberry Pi to Jetson. I know there's a way of thinking about this as tiers. Can you walk me through what those tiers look like and what you'd use each one for?
There are 3 tiers, and they're genuinely different in capability, cost, and what you deploy on them. Tier 1 is microcontrollers, the smallest, cheapest, most constrained hardware. Think Arduino, Raspberry Pi Pico, or a tiny sensor embedded in a machine. These devices have kilobytes of RAM, run on milliwatts, and cost under $5. The AI you run here is called TinyML, highly compressed, quantized models for basic classification or anomaly detection. A vibration sensor that knows the difference between normal machine operation and the specific signature of a bearing about to fail. A microphone that detects a single keyword and wakes the main processor. That's Tier 1. Tier 2 is edge servers, more powerful systems deployed locally, not in the cloud. A server rack at a hospital, a compute module on a factory floor, a dedicated node at a retail location. These can have GPUs or NPUs, run mid-size models with full accuracy, and handle complex inference tasks, real-time video analysis, multimodal pipelines, continuous stream processing. Tier 3 is near-edge devices, smartphones, tablets, modern laptops. These have the dedicated AI accelerators I mentioned, neural engine, hexagon NPU, tensor chip, and are increasingly capable of running large models locally. There are 7 billion parameter language models running entirely on phones right now, today, in production applications. The architectural question when you're building an edge AI system is always, which tier does this task belong to? Because putting a Tier 2 workload on Tier 1 hardware doesn't work, and putting a Tier 1 workload on Tier 2 hardware wastes resources and power.
TinyML is something I find fascinating because the constraints are so extreme. Kilobytes of RAM, milliwatts of power. What can you actually build with that? And how do you even get a neural network to run in that environment?
The canonical TinyML example is keyword spotting, detecting a wake word like Hey Siri or OK Google. That process runs on a dedicated chip that consumes under 1 milliwatt, which is why it can listen continuously, all day, on a battery that lasts a year. The chip runs a small neural network, maybe 100 kilobytes of weights, looking for the specific acoustic pattern of the wake word in a rolling window of audio. When it detects a match, it wakes the main processor. Everything about how you get a model to run in that environment comes down to compression. You start with a model trained at full precision, 32-bit floating point. You then apply quantization, which converts the weights to 8-bit integers or even 4-bit. This cuts model size by 4 times and speeds up inference dramatically, with minimal accuracy loss for most tasks. You might also apply pruning, removing the least important weights, and knowledge distillation, where a smaller model is trained to mimic a larger one. The tooling for this has become genuinely accessible. TensorFlow Lite for microcontrollers handles the runtime. Edge Impulse is particularly impressive. It's a platform that walks you through capturing sensor data, training a model in the cloud, quantizing it, and deploying it to an Arduino, Raspberry Pi Pico, or STM32 board. The whole pipeline, through a browser interface, no deep ML expertise required. TinyML applications include gesture recognition in wearables, vibration anomaly detection in industrial machines, air quality monitoring in sensor networks, and fall detection in medical alert devices. All running on hardware you'd barely notice is there.
Okay, let me push back on this a little. Because there's a counterargument I hear, which is, cloud AI is simpler. You have the latest models, unlimited compute, and someone else manages the infrastructure. Why would a developer go through the pain of optimizing models for edge hardware when they can just call an API and be done with it?
That's a completely valid point, and honestly, for many applications, cloud inference is the right answer. If you're building a web app that uses AI for text classification, and your users have reliable internet and can tolerate 200 milliseconds of latency, call the API. I'm not arguing that edge AI replaces cloud AI universally. The argument is much more specific. Edge AI is the right answer when your application has any of these requirements. You need latency under 50 milliseconds. You need to operate without network connectivity. You're processing sensitive data that cannot leave the device, or you're running at a scale where the bandwidth or compute cost of cloud inference becomes prohibitive. Let me make the cost argument concrete. Imagine you're processing continuous video from 10,000 retail cameras, looking for planogram compliance, whether products are in the right shelf positions. If every camera sends every frame to the cloud, you're talking about enormous bandwidth costs and enormous compute costs. But if you run the inference model on embedded hardware in each camera, the cloud never sees raw video. It only receives structured events. Product X is out of stock at store Y. Detected at timestamp Z, the per-device inference is essentially free after the hardware investment. That economic argument scales very differently from cloud inference, and it's why companies running at IoT scale consistently choose edge. The simplicity argument is real, cloud is simpler to start. But simplicity isn't the only dimension that matters in production.
The privacy angle is one I don't think gets talked about enough. When you process data on the device, the raw data never leaves. That's a big deal for healthcare and financial applications. What does that actually look like in practice?
Healthcare is the clearest example. Continuous glucose monitors and ECG patches now run anomaly detection locally. The device analyzes your heart rhythm and alerts you to a potential arrhythmia without your raw EEG data ever leaving the device. The only thing transmitted is the alert, a structured event, not the underlying biometric stream. From a regulatory standpoint, this is enormously valuable. HIPAA compliance becomes simpler when you're not transmitting raw patient data. From a trust standpoint, patients are more comfortable knowing their heart data isn't flowing through a cloud somewhere. But the privacy argument extends beyond healthcare. Voice assistants that process speech on device never send raw audio to a server. That's why Apple emphasizes Siri processing on device. If the processing is local, there's no server logging your voice commands. Keyboard input prediction on phones, face unlock health tracking. These are all edge AI applications where the privacy benefit is that the inference happens before any data transmission occurs. For developers, this opens up applications that would have been regulatory or reputational minefields with cloud processing. A mental health app that analyzes speech patterns for clinical insights. A financial app that evaluates fraud risk signals from local behavior without sending transaction patterns to a third party. The edge privacy boundary is genuinely enabling categories of applications that couldn't exist otherwise.
Let's talk about what's actually in production today, because I think that's where the reality check happens. What are the most impressive real-world deployments of edge AI that you'd point people to?
There are a few that I think illustrate different things. John Deere See Spray system is the one that genuinely surprised me. They mount computer vision cameras on agricultural sprayers. As the sprayer moves across a field at 12 miles per hour, the cameras are running a vision model that distinguishes crop plants from weeds. At that speed, in real time, with enough confidence to selectively spray only the weeds. The model runs entirely on board the sprayer. It's reduced herbicide use by 77% in trials. There is no version of that system that works through cloud inference. The latency and connectivity requirements don't allow it. BMW and Toyota both run defect detection on their production lines, a camera at each assembly station running a vision model that flags scratches, misalignments, and missing components in milliseconds. The line moves at 60 cars per hour. A cloud-based system would introduce enough latency to become a production bottleneck. Apple's photo pipeline is one most people use every day without thinking about it. Every photo you take on a modern iPhone is processed by a local AI pipeline. Scene detection, HDR computation, noise reduction, portrait mode depth estimation, optical image stabilization. Apple's Core ML runs over 30 models sequentially in under 100 milliseconds, entirely on the neural engine. No server, no network call, no upload. The computation completes before you've even lowered the phone. And then there's Amazon's shelf monitoring deployment. Cameras on retail displays running inference on embedded chips in the display hardware itself, checking planogram compliance continuously. No cloud involved in the detection loop. The cloud only receives alerts.
Let's get into the software side, because I think that's where most developers actually get stuck. The hardware story is compelling, but getting a model from your training environment onto a Raspberry Pi or a Jetson, what does that actually look like? What's the pipeline?
The edge deployment pipeline has 4 steps, and each step is critical. Step 1. Export to an interchange format. You train your model in PyTorch or TensorFlow, whatever your team uses. But you can't just take that model and drop it on edge hardware. You export it to ONNX, which stands for Open Neural Network Exchange. ONNX is hardware agnostic. The same exported model can run on CPUs, GPUs, NPUs, and TPUs with the right runtime. It's become the standard intermediate format precisely because it decouples the training framework from the deployment target. Step 2. Optimize and quantize. Full precision models use 32-bit floating point weights, too heavy for most edge hardware. Quantization converts weights to 8-bit integers or 4-bit. This cuts model size by 4 times and inference time by 2 to 4 times, with minimal accuracy loss for most tasks. ONNX runtime, TensorRT, and TensorFlow Lite all do this automatically through their optimization passes. Step 3. Select a runtime. ONNX runtime is the most portable. It handles hardware acceleration across CPUs, GPUs, and NPUs on Raspberry Pi, Jetson, Windows, and Mac. TensorFlow Lite targets mobile and microcontrollers. TensorRT from NVIDIA maximizes throughput on Jetson devices specifically. Core ML is Apple's on-device runtime for iOS and macOS. Step 4. Deploy and update. Edge models need to be updated without physically touching the device. Over-the-air update frameworks like Baelna, AWS Greengrass, and Azure IoT Edge handle the distribution, versioning, and monitoring of model updates across device fleets. If you're deploying to 100,000 factory sensors, you need infrastructure for pushing a new quantized model to all of them when you retrain. That last step is the one teams underestimate. The operations of edge AI is as complex as the modeling.
For a developer who's convinced and wants to start, maybe they have a project idea, or their company is thinking about adding on-device inference to a product. What's the actual starting point? What do you do in week 1?
Week 1, get ONNX runtime running on your target device with a small model. That's it. Don't try to solve your full production problem first. Take a pre-trained image classification model, MobileNet v3, EfficientNet Lite, something under 10 megabytes, export it to ONNX and run it on a Raspberry Pi 5 with ONNX runtime. The Python API is genuinely 3 lines. You load the model, you pass it an image array, you get back predictions. Measure the inference time. That number tells you what you're working with on that hardware. If you need mobile, Core ML on iOS and TensorFlow Lite on Android both have official converters from ONNX. You can integrate on-device inference into a native app or React Native in an afternoon once you have the model format right. If you need microcontrollers, start with Edge Impulse rather than hand-rolling the toolchain. It abstracts the entire pipeline behind a browser interface. The key design principle that I'd emphasize above everything else: test on your actual target hardware early. The performance profile on a Jetson Orin and a Raspberry Pi 5 are dramatically different. A model that runs at 60 frames per second on the Jetson might run at 4 frames per second on the Pi. Don't build your product assumptions on benchmarks you read online, measure on your hardware. Model size is the primary lever, under 10 megabytes as a starting point. Quantize immediately, profile before you optimize, and resist the temptation to start with a large model and try to compress it down. Start small and grow up if you need to.
Here's something I want to debate with you a bit. The framing of edge versus cloud AI sometimes feels like it's being set up as a competition, like one is going to win. But is it really a binary, or is it more complicated than that?
It's definitely not binary, and you're right to push on that. The real architecture in most sophisticated systems is a tiered approach, different parts of the inference pipeline running at different layers. Think about how a modern voice assistant actually works. A tiny model on the device's dedicated audio chip listens for the wake word, consuming under a milliwatt. That's Tier 1 edge. When it detects the wake word, it wakes a more capable on-device model, running on the neural engine or hexagon NPU. That does the first pass of intent classification. That's Tier 3 near edge. Only if the on-device model determines that the request requires information or compute that isn't available locally does it make a cloud API call. So you have 3 tiers of compute, and the system dynamically decides where each unit of work runs. This pattern is called triage inference, routing each inference task to the most cost-appropriate compute layer. Simple tasks stay at the edge. complex tasks escalate to the cloud. The key engineering challenge is building the triage logic, deciding what goes where, and managing the consistency of results across layers. But the payoff is a system that's both responsive and capable. It doesn't pay cloud latency for tasks it can handle locally, and it doesn't hit a capability ceiling when it encounters something complex. The future of AI infrastructure isn't edge replacing cloud. It's tiered intelligence, compute, distributed appropriately across the spectrum from milliwatt microcontrollers to hyperscale data centers.
I want to ask you about where this is going. Because if the hardware is getting better and the models are getting more efficient every year, what does Edge AI look like in 2 or 3 years? What's the next interesting thing?
3 things I'm watching closely. First, federated learning at scale. Right now, when you train a model for edge deployment, you train it centrally on data you've collected, then push the model to devices. Federated learning inverts that each device trains on its own local data, and only model gradients, not raw data, are shared with a central aggregator that combines them. This means you can continuously improve a model across a fleet of devices without ever seeing the raw data from any individual device. Apple uses this for keyboard prediction improvements. The medical device space is very interested in it for obvious privacy reasons. The tooling is still maturing, but this is a genuinely important pattern. Second, on-device fine-tuning. Today, you fine-tune a model in the cloud and push the weights to devices. Within 2 years, I expect to see production systems where devices fine-tune their own model weights on local data, personalizing a shared base model to individual usage patterns, on-device, privately. The compute and memory requirements have been the blocker, but the hardware trajectory suggests this becomes feasible on high-end mobile silicon in that timeframe. Third, multimodal edge inference. Running models that jointly process video, audio, and sensor data on a single edge device in real time. The applications in robotics and autonomous systems are significant. The models exist. The edge hardware capable of running them efficiently is arriving now.
All right, let me try to pull this together. We've covered a lot of ground. If someone is walking away from this conversation and they want the 3 or 4 things to hold on to, what are they?
First, Edge AI is about running models on the device where data is generated. No cloud round trip, no network dependency. The benefits are lower latency, offline capability, and better privacy. These aren't theoretical benefits. They are the enabling conditions for entire categories of applications that cannot exist with cloud-only architectures. Second, specialized hardware is what made this practical. NPUs, TPUs, neural engines, silicon designed specifically for the matrix operations neural networks require. Every modern phone and laptop has dedicated AI acceleration. The Raspberry Pi 5 plus an $8 Google Coral USB accelerator gives you 4 trillion operations per second at a $35 starting point. Third, the software pipeline is the same regardless of target hardware. Train in PyTorch or TensorFlow. Export to ONNX. Quantize to 8-bit or 4-bit. Choose a runtime, ONNX runtime for portability, TensorRT for Jetson, TF Lite for mobile, Core ML for Apple. Deploy with an OTA framework. Fourth, it's not edge versus cloud, it's tiered intelligence. The right architecture routes each unit of work to the most appropriate compute layer, from milliwatt microcontrollers to hyperscale data centers. The engineering work is designing the triage logic that makes that routing work correctly.
If people want to go deeper, where should they go? Any specific resources or starting points?
Our YouTube channel just published a visual explainer on Edge AI. That's V029, Edge AI Explained, which covers the hardware tiers, the ONNX deployment pipeline, and real-world applications with diagrams. That's a good starting point if you want a visual walkthrough. For hands-on building, Edge Impulse is genuinely the fastest path to deploying a model on a microcontroller. Their documentation is excellent, and it's free for most use cases. For Jetson Orin development, NVIDIA's Jetson Developer Kit comes with a full SDK and a large community of tutorials. And Pete Warden's book TinyML is still the definitive reference for the microcontroller end of the spectrum. The ONNX runtime documentation is straightforward and has working examples for Raspberry Pi deployment that you can run in an hour.
5 milliseconds. That's the number I opened with, and it's the number I want to leave you with. The difference between 5 milliseconds and 500 milliseconds is not just a latency metric. It's the difference between an autonomous vehicle that can react to obstacles and one that can't, a medical device that catches arrhythmias and one that doesn't, a factory line that runs at full speed and one that waits on a network call. Edge AI exists because some decisions can't wait. And as the hardware gets cheaper, the models get more efficient, and the tooling gets more accessible, that category of decisions keeps expanding. Sam, thank you for walking through all of this. This has been genuinely one of my favorite conversations on the show. That's Bot Thoughts by Amtalk Soft. I'm Alex. If this episode was useful, subscribe wherever you get your podcasts. And if you want to support the show, buymecoffee.com/amtalksoft. It helps us keep producing independent tech content. We're back next week with another episode. See you there.